Hello and welcome to the virtual Qt World Summit. It's kind of a new thing for me. I assume you've made me half a day into it already. I'm here to talk about lessons learned from building hundreds of devices with C++, Qt, and QML. For those of you that don't know me, I'm Peter Winston. I'm the founder and chief executive officer of ICS. ICS has been around for a while and in the Qt business for a while. We've been helping companies since the Q3 days. We have a team of over 100 software developers with an average of 15 years of Qt experience. We also have a full UX design studio we call Boston UX, which works in the world of user interface design and UX user experience in order to help us build these devices. Mostly we focus on touchscreen devices built with Qt QML. We do this across lots and lots of different markets. Built everything from treadmills to coffee machines to life-saving medical devices. Done a bunch of in-vehicle systems for cars and motorcycles and boats and in-flight entertainment systems and French fry makers and ice cream makers. Lots and lots of things with touch screens that then do something. Most of them are connected to the internet in some way, and they have some device that they're controlling. Over the years, we've done this for lots and lots of global brands. Here's just a few of them. Most of them we can't talk about. We can only show you the ones that we've done. But lots and lots of projects, and I don't think there's anybody in the world that's built more devices with Qt and Qt than we have. 2 years ago, I was at the Qt World Summit talking about why projects fail. And in the time that we had been building all these devices, I looked at what were the common patterns of the projects that we've come into that succeeded and what failed. And largely, it came down to unknowns, not being able to scope the project correctly, or not being able to staff the project correctly. So those are similar pieces. The correct staff can often find the unknowns faster than the inexperienced staff. And the more you repeat something, the better you get at that particular thing. And so if you're off doing your first project, it gets very difficult. Of course, it's not surprising that there are unknowns and not surprising that there's risk and people are doing the thing for the first time, because after all, as the Qt company says, the future is written with Qt. As we say it, we help companies invent the future. But it's the same idea that we're building things that have never been built before, and as you build something that's never been built before, you're going to hit unknowns in the project as you try to pull the thing together. But I was trying to think back to why in particular is it hard to build these modern devices. And it turns out that if you just look at the HMI, which is the piece I want to focus on today, that the HMI seems pretty straightforward. It's got a graphic design with some standard controls like menus and buttons and sliders, and now with QML we can have more interactive controls that let you pinch and zoom and swipe, and that comes with some animation, and maybe the thing needs to control some device with sensors and actuators, and maybe the data is coming in real time and needs to be presented in some complicated way. But also, there's a settings dialog with Wi-Fi and Bluetooth and NFC and often a GPS, and there's an on-screen keyboard, and there's charts and video and voice and sound, and an administrative console with their own settings dialog and alarms and error logging and security, over-the-air updates, usage analytics, and the list goes on for lots of things that everybody wants to do. And when you're all done, you're still facing a user who expects a great experience, and they just want it to work. And they have their own ideas of what great means, and it may be a back button or undo or set up their own user preferences. And you're trying to do all of these things that an iPhone or an Android phone is designed to do, except you're trying to do it on real budget hardware. You're on budget hardware because the hardware guys are looking at the cost of materials, and if you're running smoothly, they chip off a couple of bucks off that that board, and you're running tight. So you're always trying to have a fabulous experience, whatever that means, on really tough hardware, and you're always on an evolving platform that the user and the marketplace is always pushing you to do one level more, one level more, one level more. And so you have this evolving target and you have a very tight hardware. And it's not surprising, lots of products hit bumps as they go. So when I try to look at why it's hard, I also look at what's in common between all these things. And what we notice is when you take any two devices and you compare them, there really isn't that much in common between any two. But when you take a group of 10 or 20 devices and you start to look at what's in common, there's lots and lots of things that we find that are required for some, but really good idea for most, or that the things that are required for the whole group largely come up over and over again in groups of them. Before I get to what those things are, I just want to say there's some project principles that I try to stick to, which are come from the whole analysis of understanding the risk in a project in order to run the project more smoothly. Find risk early if you can. If you don't find the risk early, it'll kill the project if it comes up late. Use UX to test your ideas and to nail down the specifications of what it wants to do. If it doesn't show up in the user interface, it's probably not worth doing. I mean, so one of the things to really understand is that it's the user experience is going to drive what the device does and not something that's put on at the very end. When you get in trouble on a particular thing where you think there is risk, we like to build a small prototype and just prove out that particular piece. Think that experienced staff on each of the risky or major components is critical. We like to test throughout and test in layers. And we like to reuse whenever possible, and we like to both build reusable software and reuse the software. And there are a lot of studies that show that the higher the software reuse in a project, the higher your quality will be. When I dig a layer down into the GUI, everyone talks about separating the UI from the back-end application. It's one of those things everyone talks about, but not everyone follows through with. But just as a quick tip, if you're putting application logic into your QML component, you didn't separate it out cleanly. And so in addition to separating out the UI from the back end, we try to build in more and more layers. We like to keep flexibility between those layers. A general good rule of thumb is more C++ and less QML. We like to lead with UX, and then we want the implementation to follow that UX in precise detail. So we think that the user interface designer is trying to implement what the user experience professional let out, and we want to make those pixel perfect and get all of the interactions defined well in advance. I said separate the user interface from the back end, so we like to use a particular layered architecture, QML at the top level doing visualization, and then a C++ layer that handles what's on each screen, and then the data model and communications. And at the bottom layer, we use a plug-in architecture so that we can plug in different backends, and it's going to be the final backend, which could be an MCU or your device, and then we're going to have some simulator backend, which is going to allow us to test the thing as we go. This is, over the years, we've turned that layered architecture into a reusable framework that we use on these devices. We believe in using, or that you have the the architecture, the middle layer is now gotten a little bigger to be a messaging system. And at the bottom, we put a platform layer where we have device drivers and OS support. We stick to a very strict rule of use calls when you're going down from one layer to the layer below it, and we use Qt signals when you're going up from signaling above you. We use a state machine, as I said, in that work messaging framework rules engine, and we use the state machine because it's a way of tying the user interface together with the back end in a way which is both provable and testable, but also flexible enough that we can make modifications very late in the design process to accommodate changes in the UX as they come in. And whenever we can, we try to make components reusable. So this is an example of a coffee machine. It's going to work according to the same principles. We'll put the touch screen will be controlled this way, and the actual brewing of the coffee controlled via I/O. But once you have this, coming up with another machine is actually very simple, and you can extend your brand and keep in the same architecture. It works in lots of different things. Sometimes there's a web component where there's some secure access, and you need to connect to cloud services. And in lots and lots of devices, we've seen the same basic layered architecture work time and time again. Sometimes the pieces are bigger, sometimes they're smaller, and it needs to be customized. But we use that basic architecture, and in fact, a framework that we try to use in a reusable way over and over again. But even without our framework, we've built 100 devices with just nothing more than the architecture slide I just showed you. So is there a typical HMI, and what can you extract from it? I wanted to go through how we think about a project by actually looking at an example. And this is a very rare example for me because I normally can't talk about individual projects. But sometime after a lockdown, I think in the May-June timeframe, we started working on an open source ventilator. Open source ventilator is a device that's being built right now to help in hospitals and to help COVID patients. Largely, the manufacturer is aiming this at emerging economies. It has a bill of material around $500, and they're selling it without markup. To sneak ahead to the end, just to give you an idea, this is what a main screen of a ventilator looks like. A lot of data coming from the device and displaying it to a medical professional. As someone said to me early in the process, putting the pixels on the screen is easy. Putting the pixels on the screen in a way that a medical professional can save someone's life, that's harder. So the platform for this thing is a Raspberry Pi 4, 2 gig of RAM, 10-inch touchscreen. The OS was up to us. We were choosing between a couple of things. And Toolkit, we of course wanted to use Qt and QML. And there were some questions in the very beginning about would we need OpenGL for some of the details. This is the electrical schematic. What you should notice here is that in addition to the Raspberry Pi, there's a STEM32 microcontroller. The microcontroller is actually controlling the actuators and the sensors, and that all we're going to do is talk to the microcontroller. And I think we also talk to an alarm system. So if the microcontroller goes offline, we can trigger some alarms. In another device, say a coffee maker, instead of the microcontroller, the CPU here would probably be stepped up to an IMX6, and the application would also be dealing with the sensors and the actuators. But the same architecture will work here, and we'll be able to see how you could add things in the future. So we like to start with UX design to identify the requirements. And here we have a wireframe. A wireframe is working with the customer, maybe the customer's end users. And this is drawn with a pencil, and we get some idea of what the basic things look like, and then going into more depth with each screen to try to understand what each screen does and what it might look like. And eventually, once we agree on the wireframes, we come up with some themes. The themes here were testing colors, or colorblind people, or were there issues about various countries that had issues with particular color schemes. We tried the numbers on the left and the numbers on the right, and light and themes and dark themes, and eventually came out with the theme that we did. We then had the visual designers take the wireframes and fill them in with images. At this point, these are just JPEG screenshots. Nothing here works. And we went through each of the screens, and UX ends by coming up with this flow, looking at each screen and trying to figure out what is the spot on the screen which you can touch or tap, and what are the actions that happen when the touch or tap happens, and feeding that into engineering. So once we go through this UX process, the next step is to turn it into code. And some of it's done by hand, and some of it we have, as I said, framework and tooling to do. And very quickly, we can create a user interface which does all the things that was just described in the UX document in pixel-perfect detail. So once we have that, our next step is to test the UX and the UI by building a UI simulator. The UI simulator is going to not live in a separate tool. Like, we're not using PowerPoint or some UX tool. We're actually going to use the top 2 layers of our architecture here. And instead of it going through our normal framework and talking to the actual device, we're just going to throw a simulator on the bottom, and we're going to run this on non-target hardware. Non-target hardware means not the Raspberry Pi. In fact, this thing was run on WebAssembly. So when we were done, we sent a link to the customer, and the customer sent a link to his users or his customers, and they tried it. So the simulator for every input has a matching output, and vice versa. So if you move those sliders on the right, you change the values on the left. And if you set some values on the left, which you can't see because you'd need some pop-ups for it, you change the values on the right. But it gives a person the ability to see the entire user interface, including alarms and settings and things that couldn't just be set so simply. So the results actually were good and bad. The good is he got a purchase order out of it from showing it to a whole bunch of his potential customers. And the bad was it came back with some change orders. It was a pro bono project, but it slowed down our schedule. But the changes were all good. So this is just an example where we were in middle of June and the middle of August. So middle of June, middle of August. So we went from a UX image in the middle of June to building the code, creating the simulator, shipping it to the customer, getting feedback from the customer's customer, and back to us in order to make some changes. And what you see when you look at the difference, this was a couple of doctors who gave us this input, is the numbers are more connected to the sliders. And more importantly, there were extra settings, alarm set, that we hadn't had before. And more importantly, that when you touch it, you can bring up this little micro editor, and you can adjust the values more precisely. And the whole way that micro editor comes up, and what happens if you touch it by accident, and how do you dismiss it, and what if you drag it when you meant to touch it, like all those little accidental use cases needed to be tested and wrung out. was actually quite a several-week process of building actual software and trying it. So the next thing I want to talk about is the waveform. So the waveform was the thing I thought had the most risk. Right? It's nice to have a little drawing of some sine waves or here, but really looking at it, it worried me. How fast was this thing going to be? Was it real time? Did it overwrite or scroll? Was there signal processing involved? And could QML keep up with it? I was worried because we had done a previous project, which was a heart monitor that on an IMX6, that QML didn't have the ability to keep up with it because of some issues. And so we started this right away, trying to figure out how to get that waveform performing. This is an example of the raw data that came out of the device that we were using to test. And also we had to look at how many pixels across the thing was and how many microseconds it would mean, right? We need to know how long it takes to sweep across the whole thing and how many pixels that was so that we would know how fast to go. Long story short, you know, the initial tests worked well. When we tried to integrate the thing onto the Raspberry Pi, we had problems. Went slower. We tracked it down to an OS configuration setting that one developer had that the other developer didn't have, and were able to solve the problem. The application logic. You saw the flow before from UX, and now this is the state machine coming up from engineering, and we put these things together in order to define the application layer, which is, of course, pretty simple in this application because the MCU is doing a lot of the work. The communication layer is the thing that's going to be talking directly to the MCU. So we have this message-driven GUI, so we're just going to get messages back from the named messages back from the MCU. We use this thing called Google protocol buffers, which serializes the data. The main heavy lifting is done with this thing we call a data connector. The data connector takes Q-serial port and just binds it into Qt properties. And then once they're in the Qt properties, they show up in the QML objects, no problem, and back. The other thing, the back-end message is mostly about starting the thing up and running some tests. Was all done, I think, in 4 different messages was the whole thing. It's 4 different methods in the whole thing. Then when we're done with the I/O, the next thing we do is we build a device simulator. So the device simulator is going to be a unit test of the whole system, in this case, the HMI. And so we do it with a plug-in so that we can plug the simulator in to replace the hardware or go back and forth. And this is an example of what the waveforms look like coming out of our simulator. And we do this in order to make sure that everything is working, our side is working, before we wind up integrating. So this plugs into our architecture. It goes through all of the data layers as the real device will. The only thing is, as I said, the simulator is taking I/O from the device is taking data from the simulator instead of from the device. Finally, we go through integration and testing phase, which is no different from anyone else's, although at the end, there's also what's called a validation and verification phase, which is unique to medical devices that I won't bother you with. And I guess to step back, we find that the main advantage of doing it this way is we speed up the process and we reduce risk. So using these layers forces each layer to be independent from each other, which in turn allows us to parallelize the project, which when you do many projects like this and you have people focused on each layer, it gives us a standard process and tool chain, which then helps us build even more value, and it allows us to move staff from project to project more smoothly and more easily which in turn creates more learning and more value. But the big value that doesn't come across in the architecture is that by doing it this way, we have the ability to surge on a project when it's required, where in a normal project, what kills you is when you want to surge, now you got to go out and find people and train them and bring them in the project, and that ramp-up time kills you. And by doing it this way, we think we've really diminished the cost to ramp up at the very end. To recap, I want to say you do everything you can to identify your risk early, use UX to define requirements and try to nail things down. The UI prototype I find really helpful as a way of getting input from customers. Build in layers that are testable and that are reusable. Get the hard part done as early as you can. And then as much as you can create common components that are both testable and reusable, the better you are. And if you're going to have risks, you got to either be prepared to surge or slip your schedule or limit scope. And most people aren't willing to make those trade-offs until it's too late. So thinking through what would you do if you got in trouble in advance. And I guess that's my 30 minutes of how we structure projects and things that we've learned. I think we are the best organization for helping companies build these types of things. And if you have a project that is a QT project with a touch screen that you need help on, please reach out and contact me. We also offer training courses. There's a lot of stuff that you'll see online. We're doing some virtual training courses and love to help or just figure out what we're doing in the world. I'm Peter Winston. Here's my email address and my LinkedIn. Feel free to contact me, and I hope you enjoyed the presentation.